All right, guys, here we go. Yet again, we've been torpedoed by the Snow Queen. So, trying this again. Once again, I'm teaching to a iPhone, but we're gonna do our best with this. Hopefully, you had a good spring break, whatever that means. And I'm hoping that you're keeping up, that you're nice and warm, nice and safe, and that everybody's well and healthy. I can't wait to see you guys again. Finally, again, it's been so disjointed, but can't wait to get you guys back in class on Monday. About Monday, remember, guys, remember we have a quiz. We have a quiz that's going to be on the homework in section 12.3 and 12.4. Going to be on the homework in section 12.3 and 12.4. As far as getting ready, you've got homework to do there. Just get ready for that. But I also think it's good this weekend to make flashcards up through number 57. So you're going to be flashing each other. You're going to be flashing each other. We'll take like the last 20 minutes of class on Monday to take that quiz. And then I want you reading section 12.5, which is what we're going to start today after cleaning up a little bit more with the vector cross product. Okay, so why don't we stand up, just like stand up. You know you need this just like you do in class. Stretch, okay, stretch. And maybe you want to have some water. You might even just want to kind of write down a little bit, maybe pause the video, write down a little bit of some of what we have here so that you're ready to go once I get started. So I want to take a moment, pause the video, get yourself some water, and then just kind of write down what I have here, these drawings and stuff like that. All right. Okay, I'm believing you've done that. I'm believing you've done that. So the first thing I want to talk about, this is not one of your flashcards, and it shows up occasionally, but I didn't think it was actually worth going ahead and making a flashcard of it. But if you have a dot product of a vector with a cross product, we're mixing again our two products together. Would the result be a scalar or a vector? A scalar or a vector, Ava? And you said scalar. That's exactly right. So because this would be a vector, we're dotting it with another vector, so the final result would be a scalar. Now, the fastest way I found to compute this is with that determinant idea, where now suddenly these guys are, it's actually a regular determinant of a matrix. You take your components of the first vector, throw them in that first row, and then the vector that's sitting here, remember, this is not commutative, go in the second, and then the last one goes in the last. So it's pretty easy to remember. It just, as you're reading left to right, you load your determinant of your matrix that way. And remember, as you move along columns, it starts positive, goes to negative, and then goes back to positive when we have this here. So you're gonna have your A1 here, your A2, 3, and this is kind of like where we had our IJs and Ks before. And then it's kind of the same game. You just cover up. Now you can just do it with a finger on your paper, but you cover up and then you ignore that first row and you just go back and forth along those diagonals. When you go down like this, starting from left to right, it's positive. When you go up, it's negative. And so in this case, we would have this guy, B2, C3, minus C2, B3. Okay. And that would be that first component. And again, when you're doing it, it's not so bad. You already have your minus there. You ignore this one, then B1, C3, and then up C1, B3. And I think you get the idea. I think you get the idea. So I want to talk about that because it can save time. It can save time. All right, last time, let's test you out. Last time we showed that the norm of A cross B was equal to what? Write down what follows in there. You go ahead, you write down what follows in there. The norm of A cross B is equal to what? What did we show? And we're not asking about the component form. It's more of the geometric result. Okay, so what do you have there, John? What do you have? What do you have? Did you say the norm of A times the norm of B times the sine of theta, then John, you're exactly right. You're exactly right. What's the relationship? What's the relationship between theta and A and B? Jacob, what did you say? I know. I'm talking to a camera, but I've got to pretend like you're in class that I can actually see your faces. Okay, and some of you are already bored. Some of you are already sound asleep. I can tell. Okay, so I've got my vector A. I've got B, and then that theta is the angle between them. And then what we found is that geometrically, this is the area of that parallelogram. And let me tell you again, you don't recognize how important this is. You don't recognize how important this is. When we change from different coordinate systems, when we go from our IJK to like cylindrical or spherical coordinates, and we're talking about calculus, this is really important. So the area, and you can kind of see it here. Remember, trig your friend. You know, if you've got your base here, and then you got what you have there. Okay, this norm of B sine of theta is the height of this parallelogram. The norm of A is the length. So it goes back to a classic geometry result. Okay, some inequalities that you have in your flashcards that we haven't talked about. The absolute value of A dot B. As you go along in mathematics, which you realize, and I know you're barely focused. Okay, what focus? Okay, when you go along in mathematics, equalities are a gift. Much of what's done in mathematics is done with inequalities. And these two that I'm going to show you, what we're going to derive here, that you could be responsible for on the midterm, which is coming up in a heartbeat. February is evaporating. Okay, just like the ice outside. February is evaporating. We can show that A dot B is actually less than or equal to the norm of A times the norm of B. That the absolute value of the dot product is actually less than or equal to each of the norms of each of the vectors. And this is a pretty easy result to get. Because we know that A dot B, now I know you know the components, you know, this is the product we like, A1, B1, plus A2, B2, plus A3 is 3. But geometrically, pretty much with that same angle, we showed it was equal to what? And hopefully, Brianna, you said the norm of A times the norm of B times the cosine of that exact same angle of that. And this was done through the law of cosines. But cosine, remember cosine, geometrically is on that unit circle is always between 1 and -1. Is always so the largest it can ever be is 1. So then we can change this into an inequality, just throwing that guy away, because the largest ever is going to be is 1. The largest is going to be is 1. Okay, so that follows pretty much just from the result that we had before. Now this one we're going to derive. Remember the norm of A plus B squared. Now you got your flashcards. What does the norm of A squared equal? And again, you're getting ready for your midterm. What does the norm of A squared equal? And did you say, if you said A1 squared plus A, that's not what I want. What else does it equal? And that's good to know too. And hopefully you said A dot A. Well, notice my A here is this vector A plus B. And so this is equal to A plus B dot A plus B. Now what I want you guys to do is FOIL that with your dot product multiplication. FOIL that, and remember that the dot product is in fact commutative. Use the fact that the dot product is commutative. So go ahead and do that. Do that at your seats, at your desk, okay, or wherever you're at. Okay, just blow that out, and then try to simplify as much as you can. Okay, again, this is active learning. I'm keeping you guys busy. So take some time, take a couple of minutes and actually FOIL that out. You can pause the video and just wait. Okay, I believe you're done. You've unpaused me. And so now I'm just going to catch up, just distributing, which we have a something we derived for. This is A dot A. And then we're going to get a B dot A and an A dot B, but they're commutative, so we can rewrite this as two of those A dot B's, two of those middle terms. First, outer, inner, last, okay? And then my last is B dot B. My last is B dot B. Okay, so now we're there, but again, using that same flashcard, A dot A is equal to what? Okay, and hopefully you're like, well, Dr. Warner, that's A1 squared. No. Using the same one that we did here, we can go back to, this is the same thing as the norm of A squared. Now you guys help me out. That would be the same thing as the norm of B squared. I'll get out of your way, I'll promise. And then we've got this plus 2A dot B right there. But look at this result we just showed. We showed that the absolute value of A dot B, the absolute value of A dot B is less than or equal to the norm of A times the norm of B. But remember, the absolute value of a number is always greater than or equal to a number. Like, for example, the absolute value of 5 is 5, but the absolute value of -5 is also 5. So the absolute value is always bigger or equal to what you're taking the absolute value of. Or we have this result that x is always less than or equal to its absolute value. So A dot B is less than its absolute value, less than or equal to its absolute value, but this is less than or equal to this, okay? So if Jack's less than Fred and Fred's less than Mary, the transitive property of order says, no, one more time, Doug, if Jack's less than Fred and Fred's less than Mary, I don't think we have a Fred or a Mary in the class. If Jack's less than Fred and Fred's less than Mary, what logically follows? Okay, so using our transitive property of order, this is going to be less than or equal to the norm of A squared plus 2 norm of A, norm of B, plus the norm of B squared. Now it's a little bit hard to see, but if you look at this, okay, this is something squared, and I guess I can write it like this. Imagine that you've got, and again, imagine you got x squared plus 2xy plus y squared. Just going back to high school algebra. Can you factor that? And you're like, yeah, Dr. Warren, I can factor that. That's x plus y times x plus y. And some of you are like, Dr. Warren, I couldn't have factored that. No, you can factor that. You're in Calc 3. Okay, this, if you think of x as being the norm of A and y as being the norm of B, then this is the same thing as the norm of A plus the norm of B squared. The norm of A plus the norm of B squared. Okay, so now if you're looking at this, what we've shown is this guy is equal to this, which is equal to this, which is equal to this, which is less than or equal to this, which is equal to this. Again, using that transitive property of order, we can show that the norm of this squared is less than or equal to this squared. The norm squared is less than or equal to this squared. These are both positive, okay? And so taking the square root of both sides, we can argue that the norm of A plus B is less than or equal to the norm of A plus the norm of B. So all we're doing there at the end is taking the square root of both sides, and using something about the fact that the square root function is always increasing. The the square root function is always increasing. So if this guy's less than this guy, then their square roots are also going to follow that same order. Okay, so this result is a classic result in mathematics. It's given a name. It's called the triangle inequality. It's called the triangle inequality. So say that the norm of A plus B is less than or equal to the norm of A times the norm of B. But we never really quite understood. I mean, you maybe even have heard this with absolute value. They called it the triangle inequality. But it's finally in vectors where we can understand why we would call this the triangle inequality. Because if I look at this, if I have a vector A, and then I add on to it a vector B, well, this is the vector, and you should be able to tell me. You should be able to tell me right now. This is the vector A plus B. And do you see the triangle? Do you see the triangle? That the norm, the length of this side, plus the length of that side, always has to be greater than or equal to the length of this side. Or you're not going to have a triangle. You're not going to have a triangle. Okay, so that's why it's called the triangle inequality. Okay, now I know you're bored out of your mind. I know you're bored out of your mind, but this could show up. This could show up on the midterm, so you're not bored. Okay, so make sure you understand that. Make sure you understand it. Okay, stretch. Now I had you get water, drink some water. And I'm going to do the same thing. I'm going to be a good role model here. Oh my gosh, I see the sun. I see the sun. I'm believing, guys, that's it. I'm believing this is the last time we're going to get torpedoed by the evil Snow Queen. Okay, let's finish up essentially what we're going to work on as far as the cross product is concerned, okay, before we move into section 12.5. Okay, the last thing I want to show you, and you got your homework, you get there. Now remember, guys, there in your WebAssign, down there is a personalized study plan. Within it, there's videos for other things, looking at problems and stuff like that. There's some videos associated with the book itself in the ebook. So there's lots of things to get help. Also, you're not using the Learning Center. Okay, so that's also something that's available. You can do synchronous or asynchronous. So I want you investing in the Learning Center. Also, because that resource is there, and it's just not getting used as much as it would in a non-COVID time. Okay, we talked about the norm of the cross product as being the area of the parallelogram that naturally comes from our two vectors. Now we're going to jump it up a dimension. You're like, no, Dr. Warren, let's not do that. No, we're going to jump it up a dimension. Suppose that I have three vectors and sitting in three-dimensional space. And sorry, guys, this is going to be great to have the vectors that I have in the classroom. Also, that little parallelepiped I brought in, that cardboard parallelepiped. It'd be nice to see it, but we're going to do the best we can. Okay, so I've got three vectors sitting in three-dimensional space. And I'll try to use my arms. So I have two like this, and maybe another one like that, coming up like that. Okay, that was failed. I know that failed. So one like this, and then another one coming up like that. And then you can kind of, if you just kind of make repeats of these, you got four of these like A's. Remember, it doesn't matter where they're at. Four of the C's coming around, and then four of the B's coming around. Do you see the parallelepiped? Do you see that parallelepiped that we're looking for? Now, to find the volume of this thing, what we want for any cylinder, you're like, Dr. Warren, damn it, that's not a cylinder. No, it is a cylinder. You don't like the fact that it's called a cylinder, but anytime you have a piece of area that sits in two parallel planes, and again, we connect everybody, we have something that's called a cylinder. Okay, the cylinder you're used to is called a right circular cylinder, and so you just call it a cylinder. Okay, but this is also a cylinder, and this is also a cylinder. Now to find the volume of a cylinder is defined to be, what did I use? I said define. The volume of a cylinder is defined to be the area of the two bases times the height, which is the distance between the two planes that those areas, those two parallel planes that those pieces of area sit in. Now, if you look here, we can kind of play the same game. We kind of know the area of the base by this result right here. We know the area of this base can be represented by the norm of A across the norm of B. Super fun. You're like, Dr. Wynn, that's not fun. No, that's super cool that we could actually derive that. Now, what we want to know is what's the distance between those two planes. What's the distance between this plane and this plane? Because if we could find that, then we would have our H. You're like, Dr. Warren, this is a really complicated problem. And I agree, this is really a tough question geometrically to try to figure out. I want to know the distance between this plane and this plane. And this is the trick. We can use the vector cross product. Now, what I want to do is I want to do A cross B. Now, we've argued that, okay, this is when teaching a camera, I can't see you're dazed and confused. I can't see you're not focused, okay, but I know you're not focused, okay, so focus up. Okay, we know that A cross B, that vector is perpendicular to both A and B. Did you hear the words that came out? A cross B is perpendicular to A and B. Why, Dr. Warren? Because remember, A dot A cross B is 0. So those two vectors sit perpendicular to each other. Or, if you would allow me, the cross product vector is perpendicular to the plane that contains A and B. And that's going to be the trick that we're going to use. If we do A cross B, now pull out your right hand, and you can hold it up to the video. If I do A cross B, would the vector point up or down from the plane containing A and B? And what did you say? You said up. Very good. So if I'm doing A cross B, and I don't know really how long this is, because the length of this vector here is the magnitude of this area. And so this is my vector A cross B. Now this sits perpendicular to that vector and that vector, and so it's sitting perpendicular to the plane. Okay, now the height here would be this distance right here, the distance between, and I don't think I drew that quite great, the distance between, the perpendicular distance between this vector and this vector sticking perpendicular up. And again, it would be nice if I could just have my model of my parallelepiped, and then we could actually hold something perpendicular, and you would actually get it a little better that that's what we want. We really want this distance right here, because that's going to be my height. You're like, Dr. Warren, there's no way you're going to get that. There's just no way you're going to figure that out. But I'm like, okay, guys, look at this. If I'm looking at this, here's C. It's sitting in three-dimensional space, and here's another vector. And so let me just kind of pull this out. Let me just take us back. Now I'm going to use some different vectors. I'm going to use like a vector D and a vector E. And what we want is something like that. Now, have we seen that before in this class? Can you use a word that might help me? Can you use a word that might help me remember what that is? What is that distance called? Do you remember as you get ready for your midterm? And nobody's got it? No, I believe somebody has it. Eric, what did you say? Did you say perpendicular projection? Everybody else is like, Eric, stop it. Okay, stop talking like that. This is the perpendicular projection of this vector onto this vector. And remember, it's the norm of d times the cosine of theta. Trig is your friend. Trig is your friend. But we don't want to have to find theta. So does anybody remember the flashcard that'll give me that length, that component? Does anybody remember the flashcard that'll give me that? And hopefully somebody said, Dr. Warren, I own this. It's d dot e. And remember, that would be the norm of d, norm of e, cosine of theta. But we don't want the stinking e in there. And so if we divide it by the norm of e, that's that length there. Now coming back up here, we get to twist our head around. Who's in the D and who's in the E location? And they'll be like, well, Dr. Warren, the thing we want the projection of is projecting C onto A cross B. So this guy's like my E, this guy's like my D. And so this distance here, which would be the norm of C cosine of theta, if theta is the angle between those two. If theta is the angle between those two, trig is your measuring tape, your friend. This is the same thing as C dot A cross B, C dot A cross B. Oh, Dr. Warren, look, that could be useful in something like this. That could be useful in something. C dot A cross B divided by, okay, now again, we got the thing that we don't, divided by the norm of A cross B. So that thing right there, this expression, notice we're not dealing with the angle at all. You just please accept how cool this is. Okay, this represents the height of which is the distance between the two planes, which I need for my volume formula, now remember the area is the norm of A cross B. Now notice how beautiful this is. The area here is the norm of A cross B, but the height can be represented by C dot A cross B divided by the norm of A cross B. So unbelievably, when we multiply the area times the height here, the norm of A cross B's cancel out, and we see that C dot A cross B, and then you got to be a little careful with we're talking about volume here. That represents then the volume of our parallelepiped there. And again, this is important when we talk about calculus. Moving into to volume, changes of bases and volumes. This is going to be very important. So guys, this is, again, you got to remember, Hamilton wanted to create a algebra for geometry. This thing, which is not that complicated, Now I agree, Dr. Warren, this is C, this is A, this is B, but you're smart. You can figure that out. Okay? Represents the volume of the parallelepiped. What an incredibly beautiful result. Okay. Stand up. Stretch. Look at the clock. You're like, Dr. Warren, what time did we start? Well, I think it was like around 11:35. So you have a lot more misery coming. Okay. So take a drink, maybe take a couple minutes break, go to the bathroom. Can we do this in class? No, you can't do this in class. But you can do it wherever you're at now. Just take a break, let your mind settle in, because we're going to start a new section. Okay, so go ahead and do that. And I'm just gonna, while you're gone, you can come back and fast forward through this. I'm gonna flip this board over. And you're already disappointed. We drink together. I toast you. Okay. Dr. Warren, you're so strange. That's what my daughters tell me all the time. I'm not Dr. Warren. They use the word dad. Okay. This is called Calc 3, and so far we haven't talked about calculus at all. We've just been talking about geometry. Remember with calculus is about derivatives, limits, derivatives, and integrals. Okay, of what? You're like, I don't know, Dr. Warren. You do. Limits, derivatives, and integrals of functions. And we haven't talked about functions. We haven't been dealing with functions yet. Okay, and if we go back to high school, probably the simplest function that we first ran into was our line. Do you remember that, where you had f of x? They just beat this into you. F of x equals mx plus b. Okay, that's your slope, that's your y-intercept. Now for our case here, this point slope formula is going to have more advantageous, I can't even land the English with that, is going to be better, okay, than dealing with our function, our function version. Okay, they're the same thing. I mean, if you have a point and you know the slope, you can figure out your y-intercept, okay? So if you know your slope, okay, and you have a point that's on the line, you can figure out your b. And so this is another form for a line. Now here's the disappointing thing. We're moving from the plane. This is called Calc 3. We got to extend the idea of a line, because if we don't understand a line in three-dimensional space, we're done if we start talking about trig functions in three-dimensional space, or exponential and logarithmic functions in three-dimensional space. But we really need to understand a line if we're going to extend it to three-dimensional space. Okay, so let's go back and just try to understand a line. Okay, remember, we have our points, and I think we got a pretty good understanding of that right now. Okay, we have points in three-dimensional space. Now let's start talking about lines in three-dimensional space. But let's go back and think about lines in two-dimensional space. 2 points determine a line. So hold up 2 fingers and say that. 2 points determine a line. So I've got 2 points here. One's cleverly x1, y1. Bless you, Descartes. Thank you, Descartes. And x2, y2. Now, I don't think many of you know why either one of these are actually the equation of a line. And I mean, we memorize it, we have it beat into our skulls, but we don't really understand why. Okay, and that's why I have to make sure you do before we move on. I have 2 points, and that's going to determine a unique line. You're like, Dr. Warren, I'm bored. Okay, no, you're bored because you don't know what's coming. Okay, so if I think about it, what does it mean to say that 2 points determine a line, and what's the equation of a line? Well, it means if I take any other point on the line, any other point. Now how many points are on that line? You're like, well, Dr. Warren, there's a lot. Yeah, and infinitely many. So I'm going to have to use variables. If I take any other point on the line, xy, then the line is the collection. No, don't use that symbol. That symbol means set. The line, L, is the collection of all the ordered pairs. Right in black. Is the collection of all the ordered pairs. I know this isn't exciting. Is the collection of all the ordered pairs that satisfy this equation, where m is this. So any ordered pair, now remember there's infinitely many, that satisfy this equation where m is this, all of those ordered pairs, when we look at the graph, makes that line. So this is really the definition of the line. It's a set of ordered pairs that satisfy a relationship. Now let's try to understand why that's true. And it all goes back to geometry. And so what I can do here is in Descartes' wonderful coordinate system, I can draw some parallel lines. So I can draw some parallel lines this way. I can draw some parallel lines that way. Then I can draw some parallel lines this way. And that way. And now hopefully, like Dr. Warren, I see triangles. And we can see some triangles in here. We can see this triangle, and I know there's other ones. And we can also see this big triangle right here. Now both of these have right angles in them. And these are parallel lines, so this angle's the same as this. These are parallel lines. This angle's the same as that, and I better. So if I'm looking at this, I guess they share this angle. So I look at this, here's two right triangles, and the other angles are the same. So then I know that those triangles are what? What's the word in geometry? When you have shapes that are scaled, but not deformed, we call those similar shapes. Okay, so this is two similar triangles, and what do we know about similar triangles or similar shapes? You're like, I know nothing about that. No, you do. Call it back from your gray matter. That the ratio of the corresponding sides, say that. What did you say, Dr. Warren? The ratios of the corresponding sides, say that. The ratios of the corresponding sides are proportional. Okay, so if I'm looking at that, if I look at that, if this side, I don't know what I just drew there. This side over this side over this side, big over big, has to be equal to little over little. Big over big has to be equal to little over little. But if I look at this, this is my random point, y, this is x. The distance between here and here is the same as the distance between here and here. So that y minus y1, that distance, y minus y1, over this distance, big over big, x minus x1, has got to be equal to little over little, which is corresponding little over little, which is the distance between here and here, which is y2 minus y1, and then the distance between here and here, which is x2 minus x1, okay? And we call this the symmetric form of a line. We're using symmetry in our similar triangles. Okay, so this is also an equation of a line. All the points x, y that satisfy this proportional relationship also defines L. Okay, now you don't have to do much, okay, to get here. But if you look at this, there's your M, you slide this dude to the other side, and there's your point slope formula of the line. So from now on, when your children ask, where does the equation of the line come from? You're like, they probably won't. No, you're right, they probably won't. But you will tell them anyhow, because you know, and you won't be able to help yourself. It comes from similar triangles. The equation of a line comes from similar triangles, okay? And it's a proportional relationship. You're like, Dr. Warren, why don't we use this in high school? Well, because it's more complicated than they want, okay? And there's probably people that don't know it, okay, which is even more scary. Okay, now this is the thing. When we move from lines in 2 dimensions to 3 dimensions, this form is the classic form that the Greeks gave us. Okay, so now turn to a nice fresh sheet of paper. Give yourself an x, y, z. And now imagine that we're going to do the same thing. We have 2 points sitting here arbitrarily in 3-dimensional space. Now this is going to be an x1, y1, z1. This is going to be an x2, Dr. When we're bored, y2, z2. And again, in three-dimensional space, we're going to have a unique line between these. I guess I'll draw in blue. And again, if we take any other point on the line, now suddenly we've jumped up a dimension. This is going to have 3 coordinates. And then the question is, what's L equal to? What's this L equal to? Well, you're like, Dr. Warren, I bet it's going to be a set, and you're right. All the points that satisfy what relationship? And that's what we're going to try to do for the next 15 minutes or so. We're going to try to understand what relationship would extend. I mean, you all know that if I say y equals 3x plus 2, that's a what in two-dimensional space? All the points that satisfy that is a line. You're like, Dr. Warren, I can even graph it. Watch, I can go up 2. Then I go over, every time I go over 1, I go up 3. Bam, okay? I can even graph that line. Now the thing is, this is not a line in three-dimensional space. All the x, y, z's that satisfy this is not a line. It's a plane. You're like, what are you talking about, Dr. Warren? Well, you come down here and you just graph that same thing. You go, here's this guy right there. And then you go over 1, up 3. Okay, and then you draw your line there. It's the same line that we're looking at there. But all the x, y, z's that satisfy this, we go all Dr. Strange on it, would be that plane that's going, perpendicular to the xy plane. All the points on that wall satisfy this. So the idea that you're going to extend this idea and say, okay, z is going to be equal to 2x plus 3y plus 4, and think that that's a line. We're going to find out these are planes. These are planes in three-dimensional space. Like, oh crap. Yeah, I know. Okay, so now what I'm going to do is I'm going to give your brain a break, okay? And what we're going to do is we're going to erase. I'm going to shut my mouth. I'm going to keep myself quiet, and we're going to erase. Okay, I guess we're not erasing. We're going to try to erase. This is why I hate whiteboards. Because it starts looking like the snow outside very quickly. And what we're going to do is we're going to jump back to two-dimensional space. But now we're going to attack it with Hamilton's vectors. And we're going to come back and look at the same thing. Okay, again, what I have is 2 points. I've got 2 points. And you're like, Dr. One, what are they? Okay, well, they're again x1, y1, and x2, y2. Okay, but now what I'm going to do is I'm not going to think about these necessarily as points, but I'm going to think about the vectors. I'm going to think about the vectors that connect those 2 points. Okay, and I'm going to think, maybe I'll call this the vector A, and this the vector B. Now, what would those vectors be? Now, remember, we're in two-dimensional space. What would the components of the vectors be? So you write down, what would the component, you write down what A would be equal to. And I'll start you off. I'll start you off over here. A equals, I'll help you. B equals. I've been doing all the work. You go ahead. You tell me what that would be equal to. What would the vector A be equal to? And you're like, well, Dr. Warren, you're going down the x-axis, x1. You're going up the y-axis, y1. There's no z. We're in a plane. And now you should be able to write down B. And hopefully that's what you got. Okay, no, but you're like, Dr. Warren, I'm not really, remember, we want a line. And we have these vectors here. The vector that lies on the line is where? The natural vector, and again, you gave it to a kindergartner and said, what vector, if you're calling these vectors, kind of looks more like it belongs to the line. Hopefully you're like, well, let's just connect. Let's just connect those two. Now, what vector is that? You're like, I don't know. Well, you should know, and you better know by the midterm. What vector is that? You got a vector A and you got a vector B. What vector is that? And I'll give you a clue. Is it A plus B, B plus A minus B, B minus A? What do you guys think? Which vector is that? Which vector is that? And what do you think? What do you think there? What do you think? Let me think. Who haven't I called on today? R. What vector is that? And R, did you say the vector B minus A? That's exactly right. Awesome, R. So you're like, Dr. Warren, is it really? Well, do your head to tail. A plus B minus A is B. Just do the algebra, and you can see that's there. So now if I look at this, now don't yell at me. I'm just going to get rid of this because it's going to distract a little bit from where we're going. So this is the vector B minus A. Okay. Now, let's draw the line. Let's draw the line like we have up there. So if I do that, let's draw this line. Are you following me? Are you following me? In fact, I'm actually gonna even make this a little bit better. I'm actually gonna call D the vector B minus A. So D is B minus A. It's just to make my drawing a little bit better, a little bit cleaner. Like, thanks, Dr. Warren. I can't erase. I know. So I've got this A and this D. And then this would be then, it's a little easier for us to see. This would be A plus D, but again, D is B minus A. Now let's take again any other point. Let's take again any other point on my line. And we're not going to be creative. We're just going to say that's the point XY. Now again, we're working with vectors, and let's think of the vector that points from the origin. Position vector that points to that point. Now here's the thing. Would there be a scalar? Oh no, Dr. Warren, please, my brain's fried. Would there be a scalar that would allow me to stretch D, scale, it's all in the word. Would there be a scalar that would allow me to stretch D to reach XY? Could I scale D by some scalar? Okay, and for lack of anything else, I'll use alpha D. Would there exist a scalar where if I did A plus alpha D, that I would stretch out to the point XY, or this vector would point to, this position vector, say that, this position vector would point to the point XY. How many people out there believes there would be a scalar alpha that would do that? Okay, hopefully everybody's hands in the air. Okay, probably nobody's hands in the air but mine. Okay, but hopefully everybody's hands in the air. Okay, there's going to be a scalar that I can stretch D to reach the point XY. Okay, and then what I'm going to say here is that for any point on the line, say that, for any point on the line XY, there exists a scalar where A plus alpha D would be a vector that would point to that point. And this is another way to talk about L, our line L. we can say that L, now I'm going to, is equal to all the points x, y, such that, what's that word mean? So what's that word mean? There exists, and I'm going to use t instead of alpha because that's what the book uses. There exists a t that's an element of the real numbers such that a plus td equals the vector that's pointing to xy. And that's and you're like, Dr. One, I'm getting confused. No, I know. So here, let me say, when I say line in this class, you're going to say this so many times. Just trust me, you'll get it. Okay, when I say line, I want you to say a plus td. Line. Have you already forgotten? What did I say? Okay, remember, it's simple. I say line, you say a plus td. Line. A plus td. Line. A plus td. Now, A positions the line. The job of A is to position the line. D directs the line, hence D, okay? D directs the line. The scalar t, which can be any real number, okay, hits all the points on the line. So when I do A plus td for all scalars t, I also am sweeping out my line. I'm sweeping out my line. And this is much simpler to extend to three-dimensional space. A plus td. I say line, you say A plus td. And you're like, Dr. Warren, is this really going to give us the same? Is this really going to give us the same thing that we had up here? Well, let's test it. I say line, you say, have we forgotten already? A plus td. I say line, you say A plus td. So I pick a point on the line, xy, then there has to exist a t that's an element of the reals such that A plus td hits the point that the position vector points to, xy. It's the collection of all the points where a position vector points to that point. Where there exists a scalar where a position vector points to that point. You're like, okay, Dr. Warren, but I'm still not seeing how this has anything to do with what we were doing earlier, with what the Greeks gave us. Now remember, you found A. You said A was x1, y1. B was x2, y2. Okay, so if you're looking up here, this is x1, y1 plus t times d. But now remember, d is b minus a. And here's your vector b, and here's a. So if you're doing b minus a, that's x2, y2 minus x1, y1. Now you guys defined our addition. Which in turn defined our subtraction. And so this would be equal to what vector? And hopefully you can do it. x2 minus x1, just doing what you guys told me to do. y2 minus y1. So if I come back here, this would be x2 minus x1, y2 minus y1 equals the vector xy. Now you guys defined scalar multiplication, did you not? You guys defined scalar multiplication and you defined vector addition. So doing some scalar multiplication, t hits each of these, and then what I'm going to do is just do some vector addition. So if I do this, I'll get x1 plus t times x2 minus x1, y1 plus t times y2 minus y1. That vector has got to be equal to that vector. You guys define your scalar multiplication and your vector addition. Not only that, you defined equality of vectors. You said if one vector is equal to the other vector, if and only if what? One vector is equal to vector b is equal to the vector a. I shouldn't use b and a. The vector smiley face is equal to the vector ice cream cone if and only if their components are equal. So this would mean x would be equal to, vector x would be equal to, and I guess I probably should have gone to the other side. I love dyslexia. x2 minus x1. And y would be equal to y1 plus t times y2 minus y1. Now, Dr. Warren, where are you going with this? Where are you going with this? Okay, is it true? Yes. Now, what I want you to do is do some algebra. I want you to solve both of these equations for t. What? Yeah, no, solve both of these equations for the scalar. Sometimes you might have to do that anyhow. What scalar would stretch to meet a point? That's kind of what you're trying to figure out. When you come along here and you do that, you would get x minus x1 divided by x2 minus x1, just doing a little bit of algebra, is equal to t. Now, I'm not doing dark magic. I mean, I'm just doing algebra, taking this guy to the other side and dividing. But similarly, doing the same thing, I get t is equal to y minus y1 over y2 minus y1. Again, all I'm doing, I'm not doing any black magic, just algebra. But notice, this is t and this is t. If a is equal to b and b is equal to c, by the transitive property of equality, what must be true? Well, that y minus y1 over y2 minus y1 is equal to x minus x1 over x2 minus x1. And have we had that equation? Have we had that equation on our whiteboard? Have we had our equation on our messed up whiteboard any other time today? And you're like, Dr. Warren, yes, that's the symmetric form of a line. That's the symmetric form of a line. So you see, do you see that we can actually represent, and it's much simpler. And I think visually, for me, it makes much more sense to represent a line in terms of vectors. Now again, it's not the vector. It's this a plus td is that vector. Okay? In fact, it's infinitely many. It's in a class. But it's a vector that points to the line. And the line is the collection of the points that the position vector points to. Pick a different scalar. Make it negative. Then your a plus td is going to hit that point. And no matter where you go, as long as you let t run through all the real numbers, you're going to generate this line with your a plus td the same way you did with your point slope formula of a line. Okay, so when I say line, you say, a plus td. You're like, oh crap, Dr. Warren, you're going to jump to three-dimensional space, aren't you? Yes, I am. I'm going to jump to three-dimensional space. So what I'm going to do is I'm going to flip the board over, give your brain a break. You're like, oh crap, I forgot about that. Was that actually part of today's lecture? I've been zoning. Sorry guys, I think of every student as myself. I'm talking about me. Where I would be. I know most of you pay really good attention. Okay, well that may be a lie, but I know many of you pay very good attention. This is when I would go turn on some music for us, okay? Like to just some popular music, just to, whatever popular music is these days. I would turn on some music just to get you guys awake. But then I've done that once and then I got a copyright violation, okay, sent to me. So I don't do that anymore, okay? But I'll do it in class sometime when we're not recording. Okay, stand up, stand up, stand up, stand up, stand up, stand up. Okay, we're now ready to talk about lines in three-dimensional space. So here's your job. Give yourself an XYZ. Draw yourself an XYZ. Okay, and then what I want you to do is pick 2 points, two points in your three-dimensional space. Mark one point, okay? Then just pick another arbitrary point. Mark those as x1, y1, z1, and then you know what the other one would be. Okay, now I'm going to do the same thing. I'm going to catch up with this. So I'm going to give myself a nice healthy xyz. Okay, and then what I'm going to do is I'm going to give myself 2 points here in three-dimensional space. So I'm coming out some distance x1, coming out some distance x2, coming out some distance y1. We're bored, Dr. Warren. y2, going up some distance z1, going up some distance z2. Just like what we were doing before. Okay, and then this would have the coordinates. This would have the coordinates. You like Dr. Warren? Yes, x1, y1, z1, and this would have the coordinates x2, y2, z2, and then we're going to pick an arbitrary point on our line here, x, y, z, and there's going to be a unique line that runs between my 2 points, and then anything, remember there's a big question mark, any point that satisfies some relationship, is going to be on the line. And now we're going to extend what we were doing. In two-dimensional space. Line. Have you forgotten already? I say line, I hit the ball line, you say, I hit the ball line, you say A plus TD. Line, A plus TD. Now what's D's job? Why is it called D? It's a direction vector. It directs the line. What's A's job? It's a position vector. It positions the line, okay? What's T's job? It's a scalar that really creates the line. As T runs through all the real numbers, positive and negative, it creates the line. So my L will be all the points x, y, z such that A plus TD is equal to the vector x, y, z. Okay, I kind of forgot there exists a t. That's an element of the reals. Bad. That makes that true. Do you see that beautiful extension from our two-dimensional space immediately up to our three-dimensional space? And guys, this extends to n dimensions. No, let's not, Dr. Warren. This is called Calc 3. Don't go to 4 or 5. I'm not. But do you see how this would easily extend to higher dimensions if you wanted to talk about a line? Okay, now I need a position vector and a direction vector. And probably the best thing to do is just kind of like what we were doing before. It doesn't really matter. I could go to here or here, but I definitely have plenty to choose from. I'll let this be my position vector, and then I'll let that be my direction vector. Now I could have any direction vector I wanted. Any part of this vector would work, because I'm letting t go through all the real numbers. So any part of it would work. But if you're given 2 points, you might as well just let it be the thing between them. Okay, so we'd have A plus TD. There's going to be some scalar. Now here's the question. If I wanted to find a scalar where I would do A plus TD and stretch this to meet here, would that scalar be positive or negative? I'm teaching you geometry. Would it be positive or negative? Get out of my face, Dr. Warren. Would it be positive or negative? You're like, I don't know. Okay, come on. It would be positive. Would it be bigger than 1 or would it be less than 1? Well, you're like, Dr. Warren, you're stretching it up to here. Now, if it was a point in here, it'd be smaller. T would be smaller than 1. It's back here, the point x, y you're trying to reach would be negative and smaller than 1. Why smaller than 1? Because back here, shorter than D. Okay, so if I'm thinking about it and you're just looking at this, what would the position vector be? Well, again, it would just be x1, y1, z1, vector, okay? And then if I'm looking at my direction vector, Well, it's just the subtraction of these two guys. So my D would just be x2 minus x1, y2 minus y1. I'll get out of the way. Z2 minus z1. And then if I plug those in there, anything that would satisfy a plus td equals xyz, that would be my form of the line. That would be my form of the line. Okay, and I guess let's finish class with this. Let's try to come up with the symmetric form of the line. Let's go back to the thing that the Greeks gave us, so that we can see how different this is. And the advantages this has over other line. I say line, you say a plus td. So if I did that, and I did the same thing. I've got I'm talking fast because I know I only have like 5 minutes. Okay, I'm talking fast. I've got my vector A, my D. This is my D. You can see there, which is that this was B. It's just B minus A. There's going to be some scalar that's going to stretch this guy up to reach that point, so that when I do A plus TD, I'm going to have a position vector that points to that point. And so that's what we're saying there. Okay, so now let's just look at the symmetric form of the line. It would be A, which is here x1, y1, z1, plus td, which is x2, the vector x2 minus x1. I'll be quiet. You don't need to hear me babble on. A plus td points to the point on the line xyz. Now guys, we're going to do the same thing. Do scalar multiplication and vector addition. And so if I did that, okay, I multiply by t, I add vectors, I get x1 plus t times x2 minus x1. I'm just being quiet. You don't want to hear me. This is not a 7, that's a vector sign. So we got that. Two vectors are equal. You define the equality, you define the vector addition, you define the scalar multiplication. The two vectors are equal if and only if this is equal to that component's equal to that, and that component's equal to that. And so we get, and I'm just going to do one of these, x1 plus t times x2 minus x1 is equal to x. And for sake of time, I'm believing you guys. Well, maybe I'll do the last one, and then you guys can do the one in there, z1. Now again, this scalar is the same t in all three of these. That's the same number. You're scaling d. Solve again for t. And this is algebra. I know you can do this. And guys, I'm just believing we've done it in the middle one. And so what we end up with is this beautiful extension of the symmetric form of a line. So a line in three-dimensional space isn't like what we thought it would be, like z equals 2x plus 5y plus 4. It actually is this symmetric equation y2 minus y1. So any points that satisfy this would be on my line. Any points that satisfy this would be on my line. So like for example, suppose this was 2, 4, 6. I just did your 1, 2, 3 and doubled it. And this is like 5, 7, 9. Those are the points. The equation of the line that would run between the two would have two forms. One would be x minus x1, 2, over x2 minus x1. Now let's just do 5 minus 2, 3. Y minus 4. 7 minus 4 is 3. Please don't tell me I picked 3 for all of these. What a dumb example. I should have checked it. I want these to be different. But then you get z minus 6. I'm a moron. Over 3. I'd really have chosen those better than they're never the same. They're never the same. I just was throwing numbers out. Those should be different numbers. I mean, they're right. It's correct. I just should have picked some different things so that I have different numbers in there. And so this would be the equation. This would be the equation of a line in three-dimensional space. Or another way to write it that I'd rather have us do it, it'd be the vector 2, 4, 6, which positions the line, plus t times the vector. And then again, we can just do the same thing, b minus a, and then we're going to be bored. What a dumb thing. This is a much, for me, better form of a line. And it would be all the xy's, all the points x, y, z, okay, that satisfy that vector equation. All the points x, y, z that satisfy that vector equation. So there's the extension of a line to higher dimensions. And then what we're going to do is we're going to talk about some fun things. We're going to talk about some fun things on Monday. Some beautiful geometry. Like, for example, like in two-dimensional space, two lines have to intersect. As long as they're not parallel, two lines have to intersect. But in three-dimensional space, just imagine, look at your room and imagine a line shooting here and all the different lines that are there. Rarely do two lines intersect. Rarely do they intersect. When do they intersect? When do two lines intersect? And then if they don't intersect and you want to build a column between them, where's the proper place to build a perpendicular column that would actually connect the two with the shortest amount of material? Fun question. Almost seems impossible. And lots of other things. If they do intersect, what's the angle between them? If you take a line and a point not on a line, and again, we're in three-dimensional space. You got a point, you got a line. What's the shortest distance between the point and the line? Okay, there's all kinds of fun things we're going to be talking about as we go on. What do they call it, Dr. Warren, if two lines are not parallel like this? I can see that in three-dimensional space. But what if they go like that and don't intersect? We use the word skew. We say they're skew in that case. Okay, you've had enough of me today. I know you have. I just can't see how bored you are, so I'm excited. I know you're not as excited, but I hope some of you enjoy. I hope most of you enjoy seeing this extension, even though you're a little beat up. All right. I'll see you guys. Thanks for putting up with me. Can't wait to have you back. Can't wait to see you guys on Monday. Thanks a lot.